Hello everyone, my name is Hossein Rajabi Faqihi and today I will be presenting our paper GLUECons, a generic benchmark for learning under constraint. This is a joint work with Ali Akbar Nafar, Chen Zheng, Roshanak Mirzai, Yue Zhang, Andrej Alexander Van, Tanavan, Dan Ross, and Parisar Jamshidi. Okay, so let's get right to it. So what is our intuition of doing this research and what is our drivers? First of all, we know that despite all of the progress of deep learning methods recently, there are some shortcomings. For instance, they usually fail to perform well on complex reasoning tasks and they're data hungry. So because they're data hungry, it's really hard for them to perform well on low resource data tasks. And they're sometimes actually produce some inconsistent decisions which makes them unreliable, and this has been seen due to their vulnerability under adversarial attacks. One of the many solutions out there to resolve some of these challenges is knowledge integration. In knowledge integration, we exploit both symbolic reasoning and sub-symbolic learning, and the knowledge can be expressed in many formalisms. For instance, in logic rules, knowledge graphs, context-free grammars, probabilistic dependencies, and so forth. Here we focus on a subset of these knowledge integration approaches where we have explicit knowledge about latent or output variables of the deep learning model. We're kind of like integrating soft or hard constraints and doing so during training or inference. Okay, so what is the problem with this set of solutions on knowledge integration methods? The prior research in this direction has usually evaluated their methods against no integration methods. So for instance, someone has proposed a knowledge integration method and they have only evaluated scenarios where the knowledge integration method is there versus when it's not there. Which means that we have no comprehensive study for comparing integration methods with each other. And so we have no comparative analysis on the advantages, disadvantages, and the usages of each of these methods. As a result, it's really hard to apply these integration approaches to a more diverse set of tasks by a broader community. Consider that they have a lot of implementation costs and so forth, and you cannot just blindly implement all of these methods on a new task. You have to know whether it's really fits the task, where it's really worth the extra effort that you need for implementation and so forth. It's really hard to provide a fair evaluation and comparison among the existing methods because there is no shared comparison, right? We cannot compare task A and task B using different methods. So we attribute these challenges or the existence of these challenges to 3 points. First, there is a lack of standard benchmarks with systematic baseline. So people cannot just use because there is no standard benchmark, there is no standard set of tasks that people would evaluate the proposal on that, and there is no standard baselines that people would be able to compare to. It's also pretty difficult to find appropriate tasks where constraints are applicable, so people have to usually curate a task or come up with custom tasks that would really show the usefulness of their proposal. And there's also a lack of supporting libraries for the implementation of these various integration techniques, which makes it really hard to implement them for a set of various tasks. For instance, you cannot really implement them for 10 tasks because then you have to do 10 different implementation because there's no generic implementation that you can apply to all these different tasks. So we need really libraries that can facilitate doing so. All of these challenges have made some of the important questions in the direction to still be open. For instance, it's really unclear what is the knowledge integration performance that we can get during the inference methods, during applying knowledge integration during inference, training, or both. There is no conclusive results that can show which one is better really. The influence of integration methods when combined with simpler versus complex baselines is not clear. Does it work better when only the model is simple? Does it work even on complex baselines, or does it depend on the type of constraints and so forth? So the effectiveness of train time integration models on reducing the constraint violation is also not clear. Can they still decrease the constraint violation even if they cannot improve the results, or do they improve the results but still do not decrease the constraint violation? Also, the data size impact on the effectiveness of the integration methods is not clear. A lot of recent research have just claimed that this kind of knowledge integration methods perform better when they're applied on low data regimes. But because their set of experiments is really limited and they do not have different types of constraints that are integrated, we cannot really conclusively say that their conclusion is correct. Here we want to provide a solution that kind of like solves some of these challenges and get us at least one step further in answering some of these questions conclusively. So we present GLUECons, which provides a common ground for comparison between knowledge integration methods. GLUECons is a collection of tasks for constraint integration, where we cover a spectrum of constraint complexity from basic linear constraints to complex constraints such as like first-order logics with quantifiers. And we try to have a unified structure for this collection of tasks where all of the constraints are expressed about the latent or output variables of the deep learning models, and they are expressed in first-order logic. So the selected tasks in GLUECons are 9, and we have categorized them based on the type of the constraints that they require. For instance, we have classification with label dependencies, where the task is a classification, and there are some dependencies between the output labels of the classification. For instance, we have mutual exclusivity, where we have used the MNIST dataset for digit classification, and we have hierarchical constraints in the C400 datasets, where we have like image classification, we have multi-label outputs, but there are some hierarchical dependencies between those outputs. Next, we have self-consistency in the decisions, where our model actually makes a set of like decisions about all of the examples in the dataset, and some of these examples are actually correlated to each other, and the decisions that we have about them should be consistent with each other. For instance, we have what-if question answering on the direction of causal reasoning. We have natural language inference, which a lot of you are actually familiar with, and we have belief bank, which evaluates whether a language model can actually have like consistent beliefs through asking like sequential questions, and you cannot contradict your previous answers in a subsequent question. Next, we have consistency with external knowledge, where we have the entity and relation extraction task. The external knowledge tells us that a specific entity type can only engage in a specific entity relation types. For instance, a work-for relationship can only exist between a person and an organization. We have structural consistency. For instance, we have biotagging, where we know that the B tag should always appear before the I tag and not the other way around. We have also investigated the constraints being used in an unsupervised or semi-supervised setting. For instance, we have MNIST arithmetic task, where you have actually the MNIST digit classification task, but the supervision comes from a summation of the 2 digits. So you don't really have the label of the digits. You have to use that summation to somehow retrieve or learn the correct labels of the digits. And we have Sudoku, where you are given a partially filled Sudoku table, just one table, and you have to use a set of constraints to see whether your network can actually fill the rest of these values in the table. Okay, so as here we want to evaluate the knowledge integration methods, we actually have to go beyond the task performance. So each task has kind of like specific performance, whether being like precision, recall, fun, accuracy, or whatever it is appropriate for it. We also want to evaluate additional dimensions of the method's performance. For instance, we have constraint violation, where we evaluate whether the knowledge integration methods can actually decrease the violation of the decisions given the set of constraints that we have. We have execution time, where we are going to use to see whether, like, for instance, some method is actually worth the performance gain based on the execution time that it adds to our models. Then we evaluate the performance of these models on low data regime vs a full data regime to see like which one works actually better based on each of these constraints. We want to evaluate whether these methods perform better on simple baselines versus on complex baselines. Have in mind that usually the difference between the simple and complex or the complex are the state-of-the-art methods, and in simple ones we have either like removed the effect of large language models or the pre-training and so forth. And we also want to see each of these methods, what is the level of the complexity of the constraints that they can actually express. Some of them can only do mutual exclusivity, some of them can do any linear constraints, some of them can do logical constraints, and some can do any constraints that can be represented as a program. So along all these data sets and the evaluation criteria, we also have to include baselines. So we have selected a set of methods for integration for the knowledge integration task, both during inference and training to be included as our baselines. During inference, we have integer linear programming and A-star algorithm, and during training time integration, we have selected 2 methods which try to add an additional loss term to kind of like persuade the models to generate outputs that are consistent with the knowledge that we have by integrating that additional loss value during the training. For instance, we have the primal dual method, which solves the primal dual formulation for decreasing the constraint violation based on a self-logic surrogate and minimize the loss of the task. And we also have the sampling loss method, which maximizes the joint probability of a random sample that can satisfy the constraints. Okay, so now that you know what is GLUECons and what is the all of the evaluation criteria and baselines that we're using, let's get right to it and see what is the performances that we get from all of this. First of all, this is an example of the string baseline with simple baseline. You can actually see that we have changed Roberto with Bert, we have removed Bert, we have removed CNN, and so forth. And I'm gonna actually present the results in terms of questions that we want to answer. First was what is the difference between the performance of the inference time methods with the train time methods? And we can actually see that the ILP, which is an inference time method, can actually outperforms all of the train time integration methods in most of the tasks, except one scenario when the main task itself is about satisfying the constraint. For instance, in MNIST arithmetic, we had digit I, digit B, and the label for the submission was actually the source of the supervision. So the base model was actually very weak. So you can see that baseline without the constraint integration is 9%, and adding the ILP kind of doesn't improve or even hurts the performance. But adding primal dual or sampling can kind of solve the task completely. On the evaluation of the training data size, we have actually seen that we get better results in low data regime when the constraints come from external knowledge or structure of the output. In such scenarios, knowledge can act as an additional information or compensate for the lack of data. For instance, you can actually see here in name entity and relation extraction task, on the right side, which is on low data, we have actually see better performance gains compared to the left side, which is the full data size. But the same thing, the same observation is reversed when the source of the constraints is expressing the self-consistency. For instance, in these three tasks, you can actually see the left side, the performance gain of the integration methods is higher than the right side, which left side is the full data size. What about the constraint violation? We have actually seen that the train time integration can decrease the constraint violation even if it cannot improve or hurt the performance. And we have actually seen that the sampling loss performs relatively better on decreasing constraint violation compared to primal tool. So you can see here, for instance, in the belief network consistency, even though sampling loss was kind of hurting the performance, but is also decreasing the constraint violation, or the same thing can be seen in name entity and relation extraction task. What about the complex baselines with simpler baseline effects? So we don't see a significant difference between the performance gains that we can get from these two baselines, except when the source of the constraints is external. In such cases, we get better performance gain on simpler baselines. And you can actually see here that on the right side, which is the gain on the simple baselines, we usually get better results than the left side, which is the complex baselines. Interestingly, we also see that sometimes integrating ILP with the simple baselines, which usually do not have the pre-training or the large language models, can get comparative results with the complex baselines. For instance, the causal reasoning, the simple baseline can even surpass the performance of the string baseline, or in EMR, where we have removed BERT, the ILP plus the simple baseline can get really close to the performance of BERT for the name entity and relation extraction task. What about the execution overhead? So ILP actually is an inference time, so it has an additional overhead at inference, but the overhead we have seen to be negligible because the number of the variables for a selected task is really limited, but the execution overhead will actually grow with the number of variables that you need for your task. And also we've used a really implementation-wise optimized tool to implement ILP, which is really contributing to that negligible overhead. For train time integration, we have zero cost at inference, but high overhead during training. So we have also seen that sampling is relatively more costly than primal dual because it has an additional cost of generating the samples and calculating the satisfaction. Next, we have actually seen that combining inference time and train time integration can usually get better results than each of them alone. So you can actually see here that even though the sampling loss performance was hurting, the sampling loss integration was hurting the performance, but the combination of sampling loss and ILP is getting the best performance among all of these methods. The same phenomena can actually be seen in three other tasks as well. What about the type of constraints? We actually have seen that sampling loss can express any type of constraints ILP is kind of like more expressive than A star because it usually needs conversion for different types of constraints. But the A star approach, we do not have like a generalized solution to do linear constraints or logical constraints and so forth. And even though softmax can solve mutual exclusivity, it's really not a solution for knowledge integration. So in conclusion, we presented the first collection of benchmarks to evaluate constraint integration methods named GLUECons. We provided a set of metrics for in-depth analysis or evaluation of constraint integration methods. We explored a set of baselines for such integration during both inference and training, which we have seen that the inference mostly outperformed the training time integration. And we have showed that the performance of each of these baseline methods can vary across tasks and depend on the source of the constraints. We also released the boilerplate code and the evaluations for each of these tasks to boost the future research. Thank you for listening to this talk, and please reach out to us through email or during the conference for any further discussions on this topic.